no suggestion to put the unequal clauses upside down. My name is Brian Rees. He was a PhD student, is now continuing as an unfunded postdoc in Manchester, and this is very much his work that I'm presenting. So planetary nebula orientations, it came out of pure accident. I've always found that if you do your research, sometimes you find something you were not expecting. It cannot be true and if you don't believe, but sometimes you just have to follow it and see where it ends up. And this is one of those cases. To give a bit of context, in the case of supernova remnants, not part of this conference, there is an indication that some nebulae that have what's called bilateral, not so many of them, are aligned with the galactic plane. And that the log axis is more or less along the galactic plane. And it's unconfirmed, and I would say statistically it is not yet fully convincing, but it is indicative. And I've always been wondering, since this came out back in the 1990s, talking to Ryan, whether anything like this could happen in evolved stars as well. And looking at the journals, then as always when planetaries are concerned, ignore the emails that are coming in, there are several papers in complete disagreement. There is claim that there are some alignments of planetaries with the galactic plane, Melding and Harvard, Phillips. There are several other papers that have made those claims. Caride et al. And others have very definitely saying no. There is no evidence that planetaries are anything else than random orientations. And that's what it should be. Until Whiteman and Diaz in 2008 came up with a paper that has been completely ignored. But I've really got my attention because they show that it is actually, if you look only at planetaries close to the galactic center and ignore everything else, there is an indication that there is an alignment. Again, statistically this was not convincing. But it was enough that I asked Brian to have a look at his own sample and check this. Of course, knowing that we should find the answer, no alignment was there. So the sample that we had observed an HST sample that we observed back in 2003 or so. 34 compact pulse planetary nebulae, we got images in itself in 03. We have 96 pulse planetaries observed in MDT with ME, those are the larger ones. The selections was random. For the HST, we picked every object that was 5 arcseconds or less, and then observed every second one to ensure that a random selection. The MDT sample was more complete. These numbers are after removal of foreground objects, so you only pick within 10 degrees, less than 35 arcseconds across, 6 centimeter flux, less than about 16 millijanskis. That gets rid of most of the foreground objects. There's still a little bit of confusion, will be there. Now, one of the things that Brian did, the first thing he did, he looked at his samples, came back to me and said, yes, he found an indication for alignment. I said, no, you're wrong, go back, do this and this, and it'll go away. It took him years. But after that, he told me, well, if I classify them in morphological classes, he sees a very clear effect. And what he did, he made his own morphological classification. He recalled something bipolar, and there is evidence for lobes. So this one is a bipolar. Here you can see the lobes sticking out. This one, in his classification, is a bipolar. If there is no indication for lobe, but there is an equatorial enhancement over here, so you can identify a polar axis, he calls it a polar. If there anything else, there is a long axis, but there's no indication whether it is a polar axis or not, he calls it a non-polar. So the polar plus non-polar effectively is ellipticals. Be aware, an object like this clearly has had lobes in the past, and the polar axis is this one, not this one. And that is something you have to be careful with. So looking at those specifications, what we found was the maybe not very good, that's follow the Dave Jones method of visualization 3 times. It's more important. Plots, you make lots and lots of them. Here is the complete sample of planetary nebulae in our sample, and here is the orientation angle, in galactic polar angle. And there is no evidence of any concentration there. But if you look at the bipolars only, there is a very clear concentration. If you look at the ellipticals, so the polars and non-polars together, again the effect goes away. So one of these 3 samples shows an excess of orientations near 90 degrees galactic position angle. So from the galactic North Pole. The full sample, the other classes show no preferred orientation. So after those plots, you say, yeah, but is it significant? So you can see an effect there, but is it real or not? So you do statistics, and that turns out not to be trivial, because of course your numbers are circular. So you can't use your normal KS test because that assumes a linear scale. So he read lots of textbooks on circular statistics and did a whole series of tests. The Kuiper test, actually the KS test, but then for circular variables. A Rayleigh test, where he tested against unimodality. And he had an H1 assumption of unimodal galactic position angle at 90 degrees. Potts-Hines, it just selects whether it's one semicircle has more objects than the other semicircle. And then a 1 cm squared is effectively just compares two distributions to say are they the same or not. And he, again, this took 2 years before we finally were satisfied with reality. Look at the numbers, you can't read them from there, but this is, the top line is a full sample, bipolars, ellipticals, polar, non-polars, so now we have these samples. The p-values are the ones over here. And you can see that the p-values for the bipolars are in the, well, very small to 0.02 for the least convincing test. Interestingly, it's the Hodges-Ein test that gives you the worst p-value of 0.02. But that is the one that is very low resolution, because you only compare 2 half circles. And what this tells you is that the concentration is better than that. So the higher angular resolution your method has, the better your p-value comes out. For the other samples, we find no effect whatsoever. So the bipolars are aligned, the non-bipolars are not. Which is weird, because how do these stars know about each other? They don't. They didn't even form at the same time. So the alignment is seen. This is the scale 0 to 35 arc seconds. This is the angle. You can already by eye see the concentrations here. You see it for objects more than about 5 arc seconds across, 4 arc seconds in view. Effectively, there is no relation to the size of the object. The other samples, again, you can see there's no effect there. The bipolars are typically longer than the other ones because they have the lobes. What populations are we looking at? Well, if you look at the radial velocities, again, you can't read it. This is minus 200 to plus 200 kilometers per second. The radial velocities distribution of the 3 samples are effectively the same. And the velocity distribution is such, these are pulse objects. They're not galactic disk planetaries. And we therefore see a difference in pulse bipolars to pulse non-bipolars. Causes, and this is where you start to stretch your head and say, well, maybe I shouldn't be explaining this. It is just an observational data point, throw it down in the community. 3 sigma, but so not all 3 sigma effects have survived scrutiny, but they're good enough to publish and see what happens. But papers don't like that, you have to put a cause in. So what do you say? Well, we see it in an old stellar population, the bulge, so it is not stellar rotation. No relation to the size of the planetary, that means it is not something that's imposed from the outside, because that would get worse as the objects are larger. It comes from the inside. It is not an ISM interaction, either with material or magnetic field with the ISM. Angular momentum related, yes, almost certainly. That's what we think for bipolars. But the angular momentum in a star dates from the time it formed. And so this angular momentum vector must already have been set at the time that the star was formed. So it dates from the time of star formation. And remember, if you have a binary orbit of a star that then goes around the galactic plane, the angular momentum in the binary orbit is relatively constant. It is not affected by any changes to the galactic orbit. So the orbit might evolve, but the binary orbits do not. But the galactic pulse rotates in the rest of the galaxy. The angular momentum vector of the pulse points straight up towards the pole. We find that the angular momentum vector of the binary systems, presumably, that make the bipolars point in the galactic plane. So the bipolars go, if the binary orbit go around like this, and then they move around the galactic plane like this. How is that possible? How can the stellar system get an angular momentum perpendicular to the stellar population from what it's formed? And the answer is 3 question marks. But there is a possibility, which we came up with, that is if you have a magnetic field at the time that the star is formed. Of course, the magnetic field will make it slightly easier material to contract along the field lines and slightly more difficult against the field lines. So you get a slight elongation in the star forming cloud. You need pretty strong magnetic fields for this to work, otherwise turbulence will dominate. If you then have an elongated cloud in form binaries, those binaries will be on average further apart if they fall in the direction in which the cloud is longest. And that means they have more angular momentum. So you get a net angular momentum vector set by this elongation, even though the binaries themselves have a random orientation. So that is the only effect that we come up with at the time of star formation. So a speculative suggestion would be that at the time the bulge formed, the stars of the bulge formed, there was a very strong magnetic field along the galactic plane. And to get any effect, you need at least 80 microgauss, preferably rather long. And it is much stronger than seen in the current galaxy. Although you do see values like this in starburst galaxies. So, conclusion. Preferential alignment of bipolar planetaries in the galactic bulge. The perpendicular to the galactic plane, it says here, when it is the angular momentum, is in the galactic plane. So the binary orbit from which it formed is perpendicular to the galactic plane. Statistically significant, yes, that's what our tests show. Does it mean it's true? It needs to be tested, to be honest. Related to the bulge formation, well, in that case, there should be very strong interstellar magnetic field at the time when the bulge formed. Or maybe it was imposed much later on, but I don't see how it can happen. So it is a preferential orientation of wide binaries, assuming the assumption is here that wide binaries have something to do with making the bipolars, which in itself is an assumption. So speculation, yes, but the data seems to be pretty secure. Now, the funny thing seems that there's quite a twist in binary versus magnetic field debate. I mean, what causes bipolars? Binarity or magnetic field? So we're arguing is binary is because of magnetic field. I'm arguing is magnetic field because of binaries. Thank you.
No controversy here, I'm sure.
Thanks, Albert. We think we know that many bipolars are formed from genesis, partially because of arguments about where they lie in the galactic disk, not the bulge, a low scale line, so the younger population. And yet the bulge formed, I don't know, 8, 9 gig-years ago, and these objects wouldn't still be present. So unless you've got some magnetic field that's been lasting in that sense for so many billions of years, I don't quite see how that works.
Yeah, well, the assumption that bipolars are associated with more massive stars is true in the galactic plane. It's not true in the galactic bulge. There you see plenty of bipolars in this old stellar population. There's no one-to-one correspondence. High mass means bipolar. People have been looking for alignment of planet and nebulae in the galactic disk away from the bulge, have not found any effect. So I would argue that this is a different sample. The age of the bulge is not particularly well known. We find from fitting PM populations that 5 billion year population cannot be ruled out. In fact, it seems quite plausible, but it may be up to 10.
Question from the back.
I guess the significance would be the critical issue here, right, for your result. And my question is a typical statistical question. The question is, what is the error of your error? And so wouldn't it be better to do a bootstrap?
We did. We spent 2 years doing all the bootstrapping we could.
Okay.
Yeah, so that survived the bootstrapping.
Okay. Yeah. So it's not only based on the t-test.
No. We ran every statistical test we could think of. And the bootstrapping, yes, that was pointed out straight away to us that we should be doing that.
That's done. Albert again. So we'll move to our next speaker, Andres Perez-Sanchez. This talk is on the first synchrotron jet solved toward a post-8 square.